So I'm going to talk about how we're making Postgres distributed for SaaS applications at Nile. Some of the slides are involved, so you can find a PDF if you go to the QR code. I'm also afraid of going to random QR codes, but I swear I'm not rickrolling anyone. It is, in fact, a PDF with slides. However, it is an older version of the talk. So the first half, it will be very similar. And then toward the end, it diverges. I cut out a bunch of Postgres locking internals and replaced what I think you guys are going to enjoy much more, a deep dive into how our system deals with all kinds of fun distributed error conditions. Since I was just introduced, I'm going to skip that one. OK, so we're going to talk about why even distributed DDL, why we need it, and why is it even an interesting problem to work with. And then I'm just going to go step by step over how we do distributed DDLs. Oh, by the way, I just realized that I don't know if all of you are into relational databases and know about DDLs. DDL is data definition language. If you worked with relational databases, which I hope a lot of you did, things like create table, alter table, drop table, create index, all those things are DDL. So I'm going to go step by step, show you how we do it in a distributed system, show you how we do it transactionally, and then I'm not going to talk at all about locks, and we'll skip right ahead into the failures where we'll spend a bunch of time. So at Nile, the idea is that we're taking Postgres, we're making it serverless, meaning one click to create a database, you send us a query, you get results, you don't have to worry about exactly which machines we use to run it on, and we do it specifically for software as a service. What do we mean by software as a service? Companies like this one offering their service via websites and APIs, very often replacing traditional on-prem software. And the key thing about software as a service that we try to architect the database toward is the idea that software as a service is a multi-tenant system, meaning you have a lot of customers, also known as tenants, all running on the same system, sometimes even on the same database. So there's two main ways to do it. One is to say, OK, each one of our customers gets their own either schema or user or a database. They get their own storage. Everything is very separate. You get great isolation. Sometimes you have your own CPUs. This is the high overhead customer. After a while, you find yourself managing. You can manage hundreds of databases. Can you manage thousands of databases? Can you manage 10,000? Can you manage 100,000? It gets worse and worse. And obviously, this is kind of expensive. There is more overhead per customer this way. In some lines of business, totally worth it. Customers are paying enough. In others, it's hard to make or break. Or as Deepti said a few talks back, the architecture and financials of a business are tightly coupled. So you have to think about how much an architecture decision will cost us, and can we actually charge this money from our customers? A lot of times the answer is no. The second architecture is the idea that you add to every table a tenant ID column, and you basically throw all your tenants into a single database. Very cheap, very efficient, very fun to run. Obviously, in terms of isolation, if this one machine goes down, you have a bit of a problem. The way we approach this at Nile is that we have the concept of a logical database that is striped across multiple physical databases. The physical databases can be in different availability zones, different VPCs, different regions, different cloud providers, et cetera, et cetera. And we basically place tenants on those different physical databases underneath the logical database. So we kind of get the best of both worlds. And we re-architect Postgres to give each one of those tenants its own what we call a virtual database. So they don't necessarily get their own of every object. For example, when we do create table, we want all those tenants to get a table. But they do get this database-like experience with the same isolation and privacy. So our goals in all this, especially for DDLs, is to make sure that when you do a create table as a developer, all your tenants in all their virtual tenant databases will get the same table at same time, time is a difficult concept in distributed system, but we're trying to bound the amount of time in which things are uncertain, and we'll talk about the ways in which we do it. And we want to get a native Postgres behavior. And Postgres is really cool in the way that it allows DDL to be part of a transaction. So you can do begin transaction, do some selects, create a table, do some inserts, maybe create another table, add an index, all those things. And if any of it fail, you can always roll back and none of this stuff will stick. Great for testing. It sounds really cool. It's amazing how many databases do not have this property. But we're trying to be Postgres, so we have to have it. And then we also want it to be transparent. So the developer does create table as he would in any other Postgres and does not have to know that we actually distributed this stuff. It doesn't sound all that difficult, but as we discovered, and I think that's the rule number one of distributed systems, everything is always a lot harder than initially and naively you believe it is going to be. It is very, very hard to even estimate how difficult the problem you're getting into is going to become. So let's start with just how we do it, step by step. If you ever wanted to write a Postgres extension, you're also going to get right now a quick introduction on writing Postgres extensions. So the components we have in the system. So we have Postgres, a bunch of them. And then we have the Nile DDL extension. This is the part that we do that plugs into Postgres. And in addition to those, we have a transaction coordinator. This is the thing that is responsible for managing distributed transactions. And the way that extensions work is that they have to hook into parts of Postgres. When they come up, they register, they have to tell Postgres, when something happens, call me. And there's a bunch of hooks that you are supposed to hook into. In our case, we wanted to get notified every time a DDL happened. We hooked into something called process utility hook. We're called every time a utility runs. What is a utility in Postgres? Turns out that utility is absolutely literally everything. With the exception of select, insert, update, and delete. Those are not utilities. Everything else is a utility, which puts us in a great place. We get called all the time, so this is fantastic. And in this example, when someone does create table, we get called. What do we do when we get called? First of all, we need to know that this is actually intended for us. Utility is everything, so we need to know that we're actually getting a create, a delete, and alter. After that, there is a bunch of create, deletes, and alters that we don't actually support yet. We raise an exception on those. And the third thing we do is look at the statement and figure out which locks we're going to need. I'll explain why in a second. But it sounds like it's easy. Create table. Worst case scenario, it probably locks what? One table? No. Turns out that create table can lock a lot of things. You create a table, but then you say you want a primary key. Well, you need a table and an index, right? And a constraint. You have a foreign key constraint. You need to lock that entity, but also the other table that the foreign key refers to, because you have to do all those validations. So you end up actually with a lot of locks. We extract them, and then we start distributing things. First thing, if we got a DDL and we're not yet in a transaction in that session, we start a distributed transaction. First thing we do. Second thing, we take locks, and we take them in a predefined, predetermined order on all the machines. And the order of the machines is also predefined and predetermined. All this to avoid the deadlocks that come because one process takes a lock here and waits there, the other takes a lock there and waits here. It gets messy, so we make everything deterministic. Now, taking locks at the first step of executing a DDL is a well-known Postgres optimization tip that we kind of get out of the box for our users. Why is it important? Fail fast, fail early. Last thing you want is to hold the lock and then wait a bunch of time and discover you cannot do something while everyone else is waiting for the lock that you're holding. So we want to discover if something is not going to work. We want to discover it very early in the game. We are trying to take all the locks at that point. OK, we got the locks. What's next? Well, we actually need to distribute the actual command, right? So create table goes everywhere. Once create table went everywhere, we basically, remember, we're still in a hook. We got called before the original create table got processed. At some point, we need to tell Postgres, you know what, go ahead and actually create this table. This is when we do it. And in parallel, when I say wait for the distributed query, we actually tell the transaction coordinator, OK, start telling those machines to actually run the distributed query. So transaction coordinator distributes it everywhere. All those other Postgreses get create table. What do they do now? Well, they call the process utility hook, which is us, but we immediately pass it along. We know that this was a command from the transaction coordinator, not from a real user. We pass it along and tell Postgres, hey, go ahead and create the table on all those machines. That's it. Thanks for coming for my talk. We distributed the DDL. Well, not quite, right? I left out the actual fun part, which would be the transactions. So let's see how we do transactions. The first thing we thought on how to do transactions was the idea that, remember that our utility hook, which we already hooked into, it actually gets everything that is not select, insert, delete, or update, which means that we get begin, we get commit, we get abort, we get rollback, everything we need to do a transaction, right? Turns out that it's both too much and not enough at the same time. It sounded like a great idea, and it turned out to be a bad idea that probably came from a manager, and therefore smarter engineers, which are the rest of my team, figured out that they should do something else. So the problems were, first of all, our system for software as service applications, it's actually OLTP. OLTP has very, very high rate of transactions. We need to deal with millions of them every second. Out of them, not even a tiny fraction happens to be DDL. We end up being in the critical path of a lot of things that we don't actually care about. Not a good idea. Second thing is that we can have a transaction without a begin. And any single DDL is in fact a transaction and has to happen transactionally. We just said that it could actually do multiple things. Create table can also create an index. It happens transactionally. We have to be able to distribute it in a transactional way. So we have to know that a commit has happened even if it does not happen explicitly. The other thing is that one commit is actually not enough. If you're doing distributed systems, you know that you need 2 phases for distributed transactional commit. You need to distribute a vote, say everyone agrees to commit, and once everyone agrees to commit, you go ahead and say, okay, now everyone can actually commit. So we're missing those 2 phases. My brilliant idea was absolutely crap. What do we do instead? It turns out that there is another callback in Postgres called it's called exact callback, but you pronounce it transaction callback. And you have pre-commit event, a commit event, which is actually a post-commit. It gets called after it was committed locally. And then if a rollback happens, you also get an abort event. Exactly what we needed, right? Pre-commit and commit gives me the 2 phases I need for doing the 2-phase commit. So this is absolutely perfect. All I have to do is kind of map them to my 2-phase commit. So the way this works is that, first of all, when the process utility called, if we don't have a transaction yet, we make sure we have a transaction. We do a begin. We also set a timeout. It's good in case we happen to have a deadlock anyway. It's good in case someone dies and does not reply on time. And having a short timeout for DDL is another Postgres best practice that we kind of built in. And then we send a bunch of DDLs. At some point, there will be a commit, either by a user or not by a user. But this hook will be called, first of all, with a pre-commit event. What do we do with a pre-commit? Well, first of all, we make up a transaction ID that will identify the commit everywhere. And then the transaction coordinator converts this pre-commit into something called prepare transaction. This is a command that is out of Postgres' 2-phase commit. Postgres itself has to be part of 2-phase commit process with other databases. Prepare transaction is the standard way of doing it. and it gives us exactly the guarantees we need. So this is out of Postgres documentation, and you can see that once a transaction has been successfully prepared, it will almost guarantee very high probability that it will be successful. So very high probability is not very reassuring if you're a distributed systems engineer. So you kind of go and ask, in what cases does it not complete successfully? And it turns out that the case in which it does not complete successfully, basically prepared commit get persisted. It gets persisted to the Postgres write-ahead log, to the data files, it's on disk. You lose it if you lose the write-ahead log. If it gets corrupted, if it gets deleted, then database crashes. If that happened, the DDL I just lost, this is absolutely the least of my problems. I just lost a bunch of data, I lost the database, it's a very difficult recovery. So what I mean by almost guaranteed to succeed is that if this is going to fail, you'll have worse things to worry about. So we're going to use this, and we're going to use the guarantee. And then after we got successful pre-commit everywhere and a successful local commit, the commit shows up at our extension. We do our own cleanup locally because things were already committed locally. We can get rid of them. We don't need anything else local. Send it over to the coordinator. It distributed the commit to the things that you prepared earlier. And that's it. Everything is great, right? Well, everything is great because I just described the one scenario in which everything is absolutely great. Some cases, things are slightly less great. What do we do in those? Well, we are a meticulous company. One of our engineers sat down, and by the way, I've been in these companies doing distributed systems since 2012 or something, so well more than a decade. This is the first time I saw someone actually do the exercise of sitting down, breaking the system into states, and detailing every single situation and what we want to do and which options we have in every single one. So this guy did an amazing job. It was useful in designing the system. It is even more useful when it's time to test the system and you can just go over the list and implement scenarios for testing. After having this list and going over it, we discovered that even though the list had, like, I don't know, 50 plus scenarios, there were actually only two types of failure. Failures that happened before the pre-commit succeeded, before the vote went through and everyone said, yes, we're going to commit. Those are easy. Not everyone agreed to commit, we can just roll back. And failures that happen after everyone already agreed to commit, those are a bit harder. Because in those situations, you are in what is known as you're doomed to succeed. You have no choice. Everyone voted, everyone agreed to commit. It's not AWS, you're not kind of disagree and commit. We all agree and we all have to commit. It's just a matter of time. In this sense, the system ends up being eventually consistent because if something happened on one of those machines, we don't have a lot of choice in terms of how we resolve it. We already agreed we were going to commit. We have to resolve it toward committing. Another thing we discovered while going over all the situations is that the problem with failures, and that was also discussed by Richard in the previous talk, is that it leads you to a lack of information. You end up with, I don't know the exact state of my transaction in one or more components because they failed. So how do we even know that the system failed, right? The transaction coordinator only knows that some Postgres failed because it started to try to say, please prepare a transaction, and did not get a response. Or it tried to say, please commit, and it never came back. We don't know, did it commit? Did it prepare? Did it fail? Did it write something to disk? Did it not write anything to disk? We have absolutely no clue. So the first order of business is that we want, when the machine came up, to have a way of knowing what is actually going on, which means that we need our own state. Luckily, we have a lot of databases lying around. So we are actually having two copies of the state, one that is the source of truth, and one that is a bit of an optimization that is used in specific cases. the source of truth for each database is locally to that database. And we have two different tables. One of them is natively by Postgres. Remember that I said that a successful prepare transaction for commit is actually persisted? It is visible in a table. And in this table survives restarts, which means that if we have a transaction that is ready for committing and not yet committed, and you query this PG prepared transaction, you will get this transaction. So this is how we know for a fact that a transaction has been prepared and the vote is yes from this machine. The second table, distributed transactions, is by us. And the way we work with it is that when we begin the distributed transaction, we do a local insert inside that transaction. What does it mean? A, while the transaction is in progress, nobody can see if there is anything in that table. This is part of ACID, right? Isolation, meaning as long as the transaction is not committed, nobody can actually read the data that it is writing. If the transaction rolls back, the row is gone. No cleanup needed. It's as if it was never written. The only case we will see anything in that table is if the transaction is successfully committed. So this is a great source of truth. Did this transaction actually go through? In addition, we have a table in the metadata database. It's like a third database, not part of the system, that basically says for each database, those are the transaction IDs that it is part of, and this is the status of each. So we can use that to speed some stuff up in recovery. In addition to the persistent state, the transaction coordinator obviously has in-memory state. For every connection, which transactions it has on this connection, what is their current status. In case that the transaction coordinator is up, we can use the in-memory state for recovery. So how do we use all this to recover? The key is that we're talking about a reconciliation loop process. We have database that just came up in one state. We have transaction coordinator in another state. We have to somehow get them to the same state. And using the rule that we have a vote when we prepare transaction, and then once everyone agreed to commit, we all commit. So the algorithm is like that. Let's say a database crashed. First of all, it has to come back up. Eventually it will, depending on how catastrophic stuff were, but eventually it will come back up. And then we check all the transactions that were in flight for this database. What is their state? Let's look at those two tables. They're all committed? Fantastic, nothing to do. They're all committed, it's already all good. He is there. If it's prepared, we need to check what was the result of the vote. Clearly, if it is just prepared, it means that it didn't get the commit, and maybe nobody else got his vote. So the vote proceeded with or without this participant. What did the other part of the system decide to do? Is it a commit or a rollback? Whatever it is, this machine, again, not an Amazon employee, it has agreed to commit because it is already prepared, and therefore it's going to commit. If someone else failed, then we can roll back the prepared transaction. And then the last one is that what if it's missing? What if the transaction coordinator in memory says that the transaction is supposed to exist, but it doesn't on this machine? Well, it means that it got rolled back. And if that got rolled back, we have to roll back this transaction everywhere. And the assumption is that because it got rolled back, it has not voted yes on prepared, and therefore the vote on prepared could not have been a yes. It has to be anonymous. And therefore, the other machines did not commit yet either. They either rolled back or are waiting. And therefore, you can actually roll back everywhere. Believe it or not, this is the easy case. The hard case is what if the transaction coordinator failed? It came back up, the databases are around, but it has absolutely no clue what's going on, who committed what, all the memory is gone, right? So we need to query all those databases to reconstruct the state. And then we use the same rule to decide what is the actual state based on these distributed snippets of state. So we look at what every database say. If for every individual transaction, all of them are committed, that's easy. We can forget it ever existed. We are done. Some of them are prepared, some are committed. we need to make sure all of them are committed. Some are prepared and some don't exist, it's a rollback. And if some are committed and some don't exist, we're in deep trouble. It means that somehow our algorithm is totally broken. Touch non-existent nearby wood has not happened yet, but this is kind of the scenarios. It's always the scariest when something happens that should not exist, right? Like, you went through all the algorithm. Is that a bug, or is my reasoning about this? Is the algorithm all wrong somehow? There is also a special case, which is an orphan transaction. The idea is that, remember that everything was around the transaction coordinator knowing about everything, pushing it out, getting the responses. But there is the origin DB, the one that actually pushes stuff to the transaction coordinator. Let's say that it started a transaction, sent some DDLs, and then went away. A minute went by, 2 minutes, a week, a month. We don't know, right? Did the developer go on vacation? Did they forget about us? Did the machine actually crash? We have no idea, no clue. Did some network packet get lost? No idea. At some point, remember, the answer for every problem in distributed system is add more timeouts. Either that or you add epochs. Those are the two solutions to everything. In this case, you basically time out. After a while, you assume that the transaction is not going to finish, and you say, OK, everyone, roll it back. What happens if this was the Postgres that died is an actual crash? It comes back up. That's fine. If most likely it rolled back locally during the crash. If it actually remembers something, like the developer came back from his 2-week vacation and now remembers and tries to commit, the transaction coordinator will basically return an error saying, what the hell are you talking about? And it will roll back anyway. So all this is great in theory. We have all those scenarios. We have all those algorithms. The crux of every distributed system is the testing. Like, the system is always as good as your ability to test it. We had a lot of scenarios that we were like, what is the probability of them ever happening? Probably 0. And on the very first day of testing, before we even got into any exciting kind of testing, just very simple testing, they happened twice. Never say what are the odds. They're not as good as you think. But we had this huge map of, we have all those scenarios, we have all those states, we have all those failures. We know what is supposed to happen. Let's test this large map, right? So first thing is that we need a way to cause bad things to happen at will. So we added some APIs for please crash, please forget the next message, like just do crazy stuff. But I'm not a fan of chaos engineering. I feel like if you end up with a problem that you cannot reproduce, you're not going to solve it. It's not very useful. It's just noise. So we wanted a way to mix things up, but be deterministic about it. And we landed with Postgres transaction isolation tests. So Postgres transactions also have the same problem. You have all those things going on concurrently. Some of them commit, write, take logs, do stuff on the tables, etc. And you need to check that no matter in what orders they run, it always ends up with the correct expected result. So we ended up using the exact same mechanism, except that some of the commands are please crash, please forget a message, etc. And then it does the interleaving for us. It creates all those permutations from some very simple scripts, which allows us to have very comprehensive test coverage. Now, it came to my attention that we have not reinvented the wheel in the sense that the Postgres transaction isolation test suite existed already and we could utilize it. But it's also 25 years old. And I've heard that in the last year, more modern, exciting, container-based approaches came to the market. They sound cool. I'm hoping to beat people working on them. And I'm hoping to compare notes about what is possible and what we need. But we are definitely looking forward to expand our test portfolio. I do believe that in distributed systems, it's very, very hard to test enough. There is no too much. And Some stuff we're leaving for the future. One of the ideas we've had, first of all, we're trying hard to minimize the recovery time. Our metadata database, the one with the optimized table, it's not very resilient. It's a single Postgres. It's as good as that. We're thinking maybe use etcd, maybe use console for that. Maybe have a cluster of transaction coordinators. Will that make things more resilient? Remember that we have systems that we don't know if they committed or not, because we have a network partition and we need to somehow move forward. Do we let users connect to those and maybe see a wrong state? How eventual consistent do we want us to be? We can evict those nodes. We can prevent access to them. We can log actual DDLs. Right now, we're just logging the transaction state. But if we log the actual DDLs, it will let us continue accepting database DDLs while we're not in a perfect state and replace them later. This would be cool. We could replicate DDLs. This is something everyone wants out of Postgres and currently doesn't exist. So this is really cool. And we can even get databases and use this log to get them up to speed. So we have all those cool things we can do. Our North Star is that we're trying to write things for software as a service developers. And one thing that we know is that they don't just randomly do DDLs. What they really do is schema migrations. What does it mean? Well, they're trying to get the database in a new state in order to support new application functionality. Usually, they either take the application down, migrate the database, and bring the application back up, or they do everything in a very backward compatible way while leaving the application up. So they migrate the database, run with it for a bit, and then they upgrade the application. And then this lets me think, hey, if we know our users are doing this, does it mean that is it even valuable to try to evict nodes? Because they may not even be trying to connect to them anyway. Maybe a better thing to do is actually work really hard on minimizing the time the migration takes, because this may be downtime for the application. So this is kind of how we think about the whole thing. And to sum it all up, we learned how extensions in Postgres work. And if you want to write an extension and want more advice, do catch me up later. I gave kind of a fraction of what I know, and I'm really excited about the extensibility of Postgres. We talked about distributed transactions, which are, of course, the fun part, and how they fail, which is more fun. And we kind of talked about software as a service and how it creates those use cases. Thank you so much for your time. And yeah, I hope I will be able to talk to every one of you about these things, because it's quite exciting, right?